Now that we went over how that public health information is collected, how is it now compiled to measure health of the population? Well, measurements that summarize the health of populations are called PHSM, and these help track health trends to make comparisons across time and regions. And these key indicators include, first off, IMR, or infant mortality rate, which estimates the number of deaths in the first year of life per 1,000 live births. Historically, IMR was the primary measure of child health, reflecting the quality of healthcare and living conditions for infants. Next up, we have our life expectancy, which represents the average number of years a person can expect to live, considering the probability of dying at each age. It's a broad indicator of overall population health, but it doesn't account for the quality of life or disabilities experienced in those years. Then you have the under 5 mortality rate, which has become a standard measure for child health in the 21st century. Here, focus on children aged 0 to 5 years, which is a vulnerable group that can be severely affected by malnutrition, infectious diseases, and other health risks. After age 5, the chances of surviving into adulthood are much higher in most countries. Next up, we have the Health Adjusted Life Expectancy, or HALE, which is a more comprehensive measure than life expectancy, which was introduced by the World Health Organization. Here, it adjusts life expectancy by accounting for the quality of those years, and the key factors include mobility, the ability to walk without assistance, cognition, mental function and memory, self-care, so daily activities such as dressing, eating, bathing, using the toilet. 4, we have chronic pain that limits function, if they do. Then there's mood, so mental health alterations that impact function. And then 6, we have sensory function, which impairments in vision or hearing that affect daily life. And when all those components are considered, the result is a health score that reflects overall well-being. So for example, if someone has a 90% health quality score, that means they lose 10% of their life over their lifetime. And then this score is then multiplied by the life expectancy. Say someone has a life expectancy of 80 years, multiply by the 90%, you get around 72 years of a healthy life. Finally, we have the disability adjusted life year, DALYs, which were developed to allow for comparisons of health impacts based on diseases and risk factors. One DALY represents 1 year of healthy life lost due to either premature death or living with a disability. Here, this measure helps assess the burdens of disease and conditions, factoring in both mortality and morbidity. Now, note some differences between HALEs and DALYs. DALYs measures the burden of disease by incorporating morbidity and mortality, allowing DALYs to be used to assess the impact of specific diseases or risk factors on a population. HALES, on the other hand, focuses on adjusting life expectancy for the quality of life, concerning aspects like mobility, cognition, and pain. It doesn't typically differentiate between specific diseases or risk factors. All right, so now we got the information compiled. Now, how do we evaluate the quality of this health information? So to start off, the internet is a primary source of health info for many people, but we know it's not always trustworthy info. So before relying on a website for health information, you should ask several critical questions to assess its quality. So first off, we have the overall site quality. Is the purpose of the site clear and easy to understand? Is the site easy to navigate? Are the sponsors clearly identified? And are advertising and sales reported from health information to avoid conflicts of interest? Next up, we have the authors. Are the authors of the information clearly identified? Do the authors have relevant credentials or expertise in the field? And is their contact information provided for further inquiries or verification? Then there's the information itself. So does the site get its information from reliable sources? Is the information useful, accurate, and easy to understand? And can you easily distinguish between fact and fiction? There's also the relevance as well too. Does the site even provide answers to your specific health questions? And is the information tailored to your needs and concerns? Then for timelines, is there a date on the content indicating when it was last written or updated? And is the information current and relevant to today's health landscape? Then you have the links itself. Do the internal links work leading to additional reliable information? Or are there external links that are to related credible sites for further learning. Finally, you have privacy. Is your privacy protected while browsing the site? And can you access health information without providing personal details or creating an account? Those are all questions you have to keep in mind. And going further in depth on the quality of information, this is the part where we have to watch out, say for incomplete misinformation or even disinformation. So starting off, what is incomplete information? Here, incomplete information is accurate information that does not provide the full picture, which therefore could be misleading. It might leave out key context or important data, which can lead to false conclusions or inaccurate recommendations. So an example of this could be a study, say if certain food causes weight loss, without including information about diet, exercise, or the sample size. Then there's misinformation, which is inaccurate or false information believed by the user to be accurate. And this often happens when data is taken out of context or poorly interpreted. So an example of this could say be a viral social media post claiming that a certain herb cures cancer without scientific backing. Many users believe it because it sounds plausible, but is factually incorrect. Then three, we have incorrect information intentionally presented to encourage specific actions, which is for typically for political, financial, or social gains. It's deliberately misleading and can be dangerous if people act on it. So an example of this could be a website promoting a weight loss supplement, claiming it is FDA approved when it is not, to push sales or political agendas. So you definitely can see how bad quality information can pop up. So you have to be careful about that. All right, now that we have our information compiled, how do we show this information? Because health information is often displayed using graphics, since they create a clear picture of what's going on in a way that's easier to understand than raw numbers or lengthy text. And to quote an old saying, a picture is worth 1,000 words. And people often prefer visuals over reading large amounts of text, and so graphics can make complex data more accessible. And now we can show this information in three ways. First up, we have our line graphs, or XY graphics, if you want the fancy term. These graphics often display data on a two-axis chart with x-axis and y-axis, often used to show relationships between two variables. So you can see, say, in a graph showing the relationship between smoking and lung cancer. One goes up, the other one goes up, for example. Next up, we have our geometric graphics, which are our bar graphs or column charts, which they often show comparisons, trends, or distributions. So here, when we're talking about a bar chart, you say comparing the rates of vaccinations across different age groups. Then you have your pie charts or slash percentage charts, which are used to show how different parts make up a whole. And they often represent proportions or percentages of a total. So in a healthcare setting, a pie chart could be showing the percentage of, say, a country's healthcare spending, how much is spent on mental health, hospital care, or preventative services. However, graphics can be misleading. Poorly designed graphics or selected data can distort the true message. For example, a pie chart may exaggerate a particular segment if the proportions are shown inaccurately, or XY graphics can misrepresent trends if the axes are manipulated. It's important to ensure that graphics accurately represent data without misleading viewers. Otherwise, you kind of run into the information problem I mentioned on the last slide about misinformation, disinformation, or incomplete information. All right, now we'll be going a little bit more in depth to say what to be careful of concerning graphics. So I have figures 3.2 and 3.3. So focusing on the left, 3.2, which is a graph of deaths in country Z per 100,000 population. Note how the y-axis on this graph goes all the way to 0, which is given a clear and accurate representation of the trend. Now if you look at 3.3 on the right, the y-axis in this graph stops at a higher point of 350, which magnifies the data and create a misleading visual representation. Although the graph uses a break symbol, which is like a little squiggly right above the 0 here, the viewer still may interpret the data as showing a much steeper increase than actually exists. So The key takeaway from this is that, say in 3.3, the data shows to appear a more rapid increase in the rate of cancer deaths, far more dramatic than 3.2, even though both these graphs reflect the same data. So here, this manipulation of the y-axis can distort the viewer's perception of the actual trend. So that's why you have to be very careful when you're looking at certain graphics. All right, so now what I have here is figure 3.4, which is showing bar charts and column charts. The nice thing about these charts is that they are a great way to display data without the risk of extrapolation, which is when we use known data to estimate unknown values or predict future trends. So back to that, an example is that on a line graph, we might incorrectly conclude that cancer deaths will far exceed those with coronary heart disease in the future based on the trend. However, with a bar chart, we only show actual collected data, preventing misleading assumptions. Also, bar charts do not require drawing lines between data points where information was not collected. So this avoids the potential for misleading values or visuals that might suggest trends where there is no data. Another reason why bar charts are effective, they are one of the best ways to present data because they are less likely to be misleading compared to other types of data graphs, like line graphs, since they clearly show data points without implying connections between them where there is none. However, while they are accurate, they can sometimes appear more complicated compared to the simpler visual formats like an XY graph. So as a result, the general public may prefer the XY graphs for the simplicity, even though bar charts are more precise. All right, so now here we're going over the pie chart. So the pie chart shows the same data, but now focus on the percentage of people who will say who will die from various diseases in country Z, for example. Now, some issues with the pie chart, they compare proportions, but they often present data from different size populations as though they are the same size, which can be misleading because death rates can differ significantly between populations, even if the total number of deaths in each group is similar. So an example of this could be a small group with a high death rate may look visually similar to a larger group with a lower death rate, which makes it harder to compare the groups accurately. So overall, these graphics are incredibly useful for conveying health information, but they must be used carefully to avoid misleading the audience. When creating or presenting the graphics, it's crucial to consider the health literacy of the intended audience. And when we're talking about health literacy, we're referring to the audience's ability to obtain, process, and understand basic health information. Because a graphic that works well for one audience might not be effective for another with different levels of health literacy. All right, so now what factors affect how we perceive the public health information? Because now it's not just about how accurately the info is presented, but also how the individual, or audience actually, perceives the information. And there are three key factors that influence this. We first have what we call the dread effect, which occurs when we perceive hazards that have dramatic, visible, and often fear consequences as more dangerous. An example of this could be people tending to fear shark attacks more than the greater risk of drowning in a pool, even though drowning is far more common. Because what's more dramatic or visible? You see a shark attack or a drowning. Think of Jaws, for example, as well. And note the dread effect is often linked to catastrophic events, like a nuclear meltdown or other rare but highly publicized disasters. Then the next issue we have is the unfamiliarity effect, where we lack personal experience with unfamiliar hazards, which tend to elicit more fear. When we don't fully understand a risk or don't have personal experience with it, we tend to perceive it as more dangerous than it actually might be. So a classic example, say, could be aliens, simply because we have no direct experience or understanding of them. Then finally, we have the uncontrollability effects, where we perceive hazards beyond our control as more threatening than those within our control. The less control we have over a situation, the more fearful we are of it. So an example here could be people often fear plane crashes more than a car crash, even though commercial flights are actually statistically safer. So in short, not only when you have the information, you have to make sure it's accurate. You have to consider how the people or say an individual is going to perceive that information. So that's another thing you have to keep in mind. All right, so next up, what types of information need to be combined in order to make the health decisions? Here, decision analysis focuses on three key types of information that must be combined to make informed health decisions. First, we have probability. What is the likelihood of an outcome? Utility. So what value or importance do we place on the outcome? And then the time. What period of time is being considered? To better understand the probability of outcomes, we need to ask, how likely is the event to occur and over what period of time? So an example, this could be a chance of developing a blood clot while on high-dose estrogen pills or birth control pills is 5%. Is that 5% per cycle, per year, or over the entire period the person is using the pill? So that can be an example there. Then there's utilities. They are important when we need to combine potential harms with potential benefits. Some outcomes greatly affect our health and can limit our future. Maybe paralysis is a scary example. While others may have a smaller impact on our daily life, so mild side effects. So we need to quantify the value we place on each outcome. A utility scale helps assign a value to these outcomes, allowing us to quantify and compare their importance. Now, when we're combining probability and utility, the goal of combining these two pieces of information is to make decisions that reflect both the likelihood of an outcome and the importance we place on it. So expected utility is calculated by multiplying the probability of an outcome by its utility. So more of an extreme example, say a new treatment gives 100% hair growth but has a 50-50 chance of causing cardiac arrest. The expected utility here helps assess whether the benefit outweighs the risk, for example. And this process is often displayed graphically using a decision tree, where you can see the probabilities and utilities associated with different outcomes, helping to visualize and compare choices. All right, so now exactly what is a decision tree? So decision trees are a visual method for displaying the benefits and harms of two or more intervention options, which they help compare outcomes by incorporating both probability and utility values. And they often have what we call two different types of nodes. So first you have what we call our choice nodes, which often take more of a square shape. These represent points where a decision is made. So this is where you choose between different interventions or options. They can also have a chance node, which is more of a circle, which represent points where outcomes occur due to chance, such as probabilities like different events or results. And by combining both types of nodes, we create a full decision tree, which can be seen in figure 3.8. Now going over probabilities, it's important to remember that the total probability of all potential outcomes at any given chance node should add up to 1, or 100%. So for example, in intervention number 1, the potential outcomes are cure or death. And in intervention 2, there's a third possible outcome, blindness. So this introduces an additional layer of complexity. Now these are just examples and so forth. So now for each outcome, like blindness in 1 or 2, we also need to know its utility value, which is subjective. So its utility can vary depending on the context or perspective. All right, so what I have here is figure 3.9, or the direction analysis, focusing on the utility of blindness. So on average, people tend to assign a utility score of 0.5 to blindness, but this can vary significantly. Some may rate it as high as 0.8, while others may rate it as low as 0.2. So in figure 3.9, what we call a decision tree calculation, we incorporate the probability and the utility score, and the expected utility is calculated by multiplying the probability of an outcome by its utility value. And this gives us a comprehensive probability that accounts for both the likelihood and the importance of each outcome. So by calculating the expected utility for each intervention, we can effectively compare the two options based on both the probabilities of their outcomes and their utility values. And these EUs allow us to assess whether intervention is the most beneficial overall. And so now back to this, we'll say we give utility of blindness equal to 0.8. So because in this case, they don't view it as much of a loss. So in figure 3.10 is showing a decision analysis where blindness is assigned a higher utility score of 0.8, which this score reflects a perception that blindness is a less impactful outcome compared to the earlier example, which was the utility score of 0.5. So as mentioned in the previous example, we calculate the expected utility by multiplying the probability of each outcome by the utility score. With a utility of 0.8 for blindness, the EU calculation for each potential outcome will be higher compared to the previous scenario with a utility of 0.5. So by comparing this new analysis with the previous decision tree from figure 3.9, we can see how the higher utility score for blindness affects the overall expected utility of the intervention options. This demonstrates how small changes in the utility score can have a significant impact on the final decision, as you may be more inclined to go with intervention 2 in this case. Now, say we go to an example, say someone who is a popular celebrity gave blindness of 0.2 because say they have so much cosmetics, they have to double take every time passes a mirror. So now for figure 3.311, blindness is given a utility score of 0.2, reflecting a perception that the impact of blindness is relatively less significant. So in this scenario, a lower utility score for blindness might drastically change the recommended intervention compared to a higher score like 0.8 or 0.5. So in this case, the decision tree helps us visually see how small adjustments in utility values can lead to significant shifts in decision making. So of course the importance of these decision trees, because they become a crucial tool for presenting and comparing the potential outcomes of different interventions, taking into account the individual's or organization's perception of the values of outcomes. And they help clarify how decisions may differ based on how an individual views the severity or importance of a particular outcome, like blindness.